Hello, everyone, and thank you for joining our webinar today. We greatly appreciate your time. My name is Kristen Pauley, and I am the Director of Marketing and Business Development at Immunochemistry Technologies, and I will be moderating our webinar. Your phone has been muted. However, we encourage and welcome your questions. Please type your question into the chat dialog box on the right side of your screen and select Send to Host. If you have any technical difficulties during the webinar, please send to host. It is my pleasure to introduce our speaker, Dr. Brian Lee. In this webinar, Dr. Lee will share information on the features of HRP and its use within colorimetric ELISA assays. Thank you, Dr. Lee.
Thanks, Kristen, for the introduction. The discussion topic that I chose for today's webinar will correlate the presence of three separate molecular structure elements of the HRP enzyme with their corresponding positive impact on the HRP's performance as a stable, high substrate turnover rate redox enzyme. To start out the slide series, I thought it would be nice, since we're talking a lot about three-dimensional structures of the peroxidase and how they influence the peroxidase enzyme's activity. This is a colorful image. This is a 3D image obtained via X-ray crystallography. It's very popular because this will appear in a lot of publications, and I thought it'd be at least a good way to get started here. The peroxidase enzyme is acquired from the horseradish root, and there are 15 known isozymes of the peroxidase enzyme. The commercially marketed form, the one you can buy from Sigma and Thermal, happen to be the isozyme C1A. The reason for that is because this isozyme HRP-C happens to be the most abundant of the peroxidase isozymes present in the peroxidase root. In fact, it accounts for greater than 50% by mass of all the isozymes present in the horseradish root. Because because of the ease of acquisition of this enzyme, and because it's easy to purify, it's been the subject of the vast majority of the research on peroxidase catalytic mechanisms. So it's easy to get, easy to purify, and that's obvious that would then be the one that people would do their research on. HRP has a high specific activity compared to three other chromogenic converter enzymes, peroxidase, alk-phos, beta-gal. It has a higher specific activity than any of the other three. The advantageous features of HRP include, once again, its lowest cost per milligram, high specific activity, rapid substrate turnover rate. The enzyme is known to have a good specific activity retention when stored in a dried or liquid state. It performs well in a variety of assay conditions. In other words, it can tolerate variations in pH and buffer composition. And a benefit of this is the peroxidase is not very specific, so it's capable of oxidizing a variety of substrates, including multiple chromogen types that can be used for enzyme immunoassay signal generation. As enzymes go, it has a very small molecular weight, and that is good because when you are conjugating to an IgG, the last thing you want to do is conjugate a very large enzyme that could possibly interfere with the antigen binding site of the antibody. So putting on a smaller enzyme will cause less interference with the ability of the antibody to bind its target antigen. HRP is a glycosylated globular protein, molecular weight ranging from 42 to 44,000. It's comprised of 308 amino acids, which accounts for roughly 34,000 of the 42 to 44,000 molecular weight of the enzyme. The secondary structure of HRP, as is obvious here, is made up of hydrogen bond-driven alpha helical structures here, as well as a couple small areas of beta sheet regions here and here. Every HRP must have an active heme group associated with it, and because the heme is a catalytic site of the enzyme, so if you don't have a functional heme group, the enzyme, can't conduct any of its redox activities. In addition to the heme, we have 2 calcium ions associated with the HRP enzyme. These calcium ions are responsible for stabilizing the structure of the planar porphyrin ring structure, and by removing the distal calcium ion from the equation, the catalytic activity of this enzyme drops way off because it's not there to stabilize this planar structure of the heme catalytic site. So that's very important. So reiterating here, calcium is completely essential for the catalytic activity of the HRP. Removal of calcium, particularly the distal calcium ion, results in pretty much a 100% drop in the catalytic activity of the HRP. There are 2 calcium binding sites, as we showed you before, one in the catalytic and one in the stability domain. HRP is a glycoprotein. As such, it has relatively large, in this case, carbohydrate moiety, which accounts for roughly 18 and 22% of the total molecular weight of the enzyme, that's quite a bit. And these I did not have a nice illustration to show you of these glycan chains popping out of the enzyme, but just go to show, but trust me that they are present, and their presence on the enzyme serves to stabilize the tertiary structure of this enzyme, which translates into enhanced activity stability. This is a side view of one of the glycan chains. There are 8 of them. They're all attached by an asparagine linkage to the protein. They're made up of N-acetylglucosamine, fructose, mannose, and xylose. They aren't all of this particular composition. They will vary depending on the glycan. This slide shows us the heme prosthetic group. The heme prosthetic group is very flat, has a flat planar structure. Every heme prosthetic group contains a centralized +3 oxidation state iron, which is attached to the porphyrin ring via 4 pyrronitrogens, and the heme is also attached to the enzyme covalently via a coordinate linkage to the histidine 170 amino acid on the protein. In addition to that, it also adheres to the enzyme portion via hydrogen bonds via these 2 propionate side chains. And because this region here is very hydrophobic, it can perform hydrophobic interactions with hydrophobic regions of the enzyme as well, so that it stays associated with the peroxidase enzyme, and does not. You can knock this off, but you got to work at it a little bit. So this is a 3D figure of the catalytic site of HRP. You've got the porphyrin ring structure here, the centralized iron, and then showing 2 essential amino acids that are responsible for not only the oxidation but also the reduction of the HRP enzyme. Histidine 42 is the primary amino acid responsible for splitting the peroxyl bond. When this is done, 2 electrons are extracted from the heme iron here, and they go to reduce the hydrogen peroxide to water and oxygen. The arginine-38 acts as more of a modulator where it controls the rate at which this heterolytic cleavage occurs. And we say it's heterolytic because if we just split this down the middle, we would end up with 2 hydroxyl ions, which is bad for the enzyme. So the enzyme has evolved to produce heterolytic cleavage, which produces water and oxygen. These are 2 substrates of HRP. Hydrogen peroxide, which is the oxidizing substrate, and in this example, I show tetramethylbenzene, one of the chromogenic substrates. So the HRP relies on this oxygen peroxyl linkage to oxidize it to allow it to start going through the redox reaction, which ends up in the final oxidation of the substrate. All the oxidative activities of hydrogen peroxide are the result of this oxygen-oxygen linkage here. When this linkage is disrupted, hydrogen peroxide acquires 2 electrons from the active site heme and oxidizes it, and this then is converted to water thanks to the electrons it acquired from the resting state heme. This is a redox reaction summary. You got the resting state oxidation heme here, and it encounters hydrogen peroxide, and when this happens, this oxidizes the resting state heme and converts it to compound 1 and water. Compound 1 has 2 electron equivalents of oxidation potential, and so it essentially it allows peroxidase to end up oxidizing 2 substrate molecules, converting them to the oxidized form. So when the electron acquired from the first reducing substrate converts the compound 1 to compound 2, and then this compound 2 still has enough oxidizing potential to convert another substrate molecule to form and if you were losing TMB, you would end up with another green substrate molecule, and the enzyme can then get back to its resting state. So this is how you get the full cycle of oxidation and then reduction back to its initial starting point. The overall reaction is 2 reduced substrate molecules, but hydrogen peroxide yielding 2 waters and 2, in this case, 2 green TMB oxidized molecules. This is kind of a global view of the redox reaction that's conducted by HRP and its substrates. Hydrogen peroxide could come in and it will oxidize the resting state heme, converting it to a iron +4 oxidation state. Plus it also has it's also converted to an oxyferro radical. So you have not only an oxidized iron here, but you have an oxyferro radical too, which accounts for the second electron equivalence that it's lost. The hydrogen peroxide, once it acquires electrons, is converted to water. Now, compound 1 is capable of oxidizing a molecule of clear TMB and converting it to the 1 electron loss oxidation state structure, which is blue-green, and it acquires an electron from that TMB and converts the compound 1 to compound 2. Compound 2 still has enough oxidizing potential to oxidize another clear molecule of TMB, converting it to the green form and acquiring a second electron. And when that does that, it goes right back to its original resting state, iron +3 oxidation. Now this slide looks at the molecular level how hydrogen peroxide interacts with the resting state heme. You have neutrally charged hydrogen peroxide coming in here. It binds to the resting state heme. It is the peroxyl linkage is cleaved with the help of this histine 42, and when this cleavage occurs, 2 electrons are extracted from this heme, and it converts this heme to a compound 1, which is highly reactive in its function. Later on, our investigators kind of said, well, the distance between here and here is just too far, so we're going to need some help, and so they said that a local water can participate in the proton transfer of from oxygen 1 to oxygen 2, and when this occurs, this destabilizes this bond. 2 electrons are acquired from the heme, and it creates a compound 1. So you have this gets split because you took a proton from this one, added this one. The 2 electrons then are used to generate water, forming the compound 1, which is reactive, is the reacting driving force of the peroxidase redox cycle. This is a close-up view, 3D view of how water participates in the proton exchange, transferring protons within this peroxyl linkage from oxygen 1 to oxygen 2. This diagram was acquired because the researchers were looking at cytochrome C peroxidase, which has it's essentially identical catalytic site, but the amino acid numbers are different. So in this case, in the yeast cytochrome, this is histine 52, but it does the same thing as the histine 42 in the peroxidase enzyme. So on the reduction side of the equation, HRP needs to get reduced back to its native state. In order to do that, it must oxidize a molecule of compatible substrate. For this particular experiment where they did this, instead of using a large substrate molecule, they used a small substrate molecule like ferulic acid. Ferulic acid has a phenolic ring structure, and that allows it to act as a electron donor. So when this binds to this site, a proton is transferred to the via the histine 42, and when that happens, an electron is acquired by the heme group, converting it from a compound 1 to a compound 2. When this occurs, the oxidized substrate gets ejected, and another unoxidized or reduced form substrate could reattach, and then the whole thing starts all over again, leaving the net result of you end up with 2 oxidized substrate molecules, and you end up with water. Now this also, because the enzyme has very high catalytic activity, this process all occurs really fast. So of the 3 structures that I mentioned in today's webinar, glycosylation is responsible for stabilizing the enzyme over time, as well as allowing it to work at elevated temperature conditions. When you remove the carbohydrate, it is not as stable to performing at higher temperatures. The heme prosthetic group, by its nature, electronically, it has a very high ability to catalyze substrate. So peroxidase has a very high substrate turnover rate because of the chemistry mechanics of the prosthetic group that it contains. In addition, there are 2 calcium ions associated with the enzyme, and they are more important than you would think, because the distal calcium is essential for the catalytic activity of the enzyme, and the reason for that is because it maintains the tertiary structure of the catalytic site, and when you can't do that, and when that tertiary structure gets disrupted, the catalytic activity of the heme just stops. So calcium is a very important component to the peroxidase redox reaction. Immunochemistry Technologies provides four different formulations of conjugate stabilizer. Each of these conjugate stabilizers acts to stabilize not only the peroxidase enzyme activity, but also the antigen binding site capacity of the antibody. So you have to stabilize this, but you also have to stabilize the antigen binding sites, or essentially this is non-functional. In order to further stabilize the peroxidase activity, you have to stabilize this porphyrin ring structure. So immunochemistry technology has added additive to make sure that this porphyrin ring structure remains in its catalytically active form. And so that wraps up my webinar today. If there's any questions, you can email them in, or I could take a couple questions right now if Kristen can help me with that.
Thanks, Dr. Lee, and thanks to everyone who submitted questions. We do have time for a couple of them. The first question, what types of assays or scenarios are better suited for using horseradish peroxidase versus alkaline phosphatase?
Horseradish peroxidase, because of the type of substrates available to it, is a much better chromogeneration enzyme as far as producing signal color in ELISA formats than alkaline phosphatase. The horseradish peroxidase substrates are, produce. They have a very high absorbance, molar absorbance, so it can create very sensitive ELISA signals. Alkaline phosphatase, in terms of its chromogen oxidation, is not as good. The substrates aren't as good. Where alkaline phosphatase really stands out is if you have a situation where you need more enhanced sensitivity, the chemiluminescence is often the answer. Peroxidase does not work very well as a chemiluminescent generating enzyme. The substrate that it interacts in the chemiluminescent process ends up poisoning the catalytic site of the peroxidase, and what you see is the slope of the curve just gradually flatten out. Now, alkaline phosphatase with its substrates, you don't see this at all. That's just a linear line out about as far as the plate reader could measure it. So there are two reasons why now peroxidase has the advantage of being small. So if you're stuck making your own conjugates, you would much rather use peroxidase as your signal generating enzyme than the big old elk phos, because elk phos is big. It's hard to separate by size exclusion column, whereas peroxidase is smaller and purifies very nicely through size exclusion chromatography. So from a make your own conjugate standpoint, peroxidase is a much better enzyme to use.
Great, thanks, Brian. Our second question, do commercial conjugate stabilizers offer any other benefit to the in-game performance of the ELISA?
Commercial conjugate stabilizers, first off, are meant to stabilize the peroxidase activity, the catalytic activity of the peroxidase. They're supposed to do that. They're also supposed to stabilize the antigen binding region on the antibodies. Now, in addition to being able to do that, commercial stabilizers should also provide, as do immunochemistry's conjugate stabilizers, a way to minimize the nonspecific binding that can occur when you have your conjugate coming in and is incubated with a plate. In some cases, the conjugate can stick nonspecifically to the plate wells, and if you add a proprietary additive to the conjugate diluent, that will prevent most of that nonspecific binding between the conjugate and the plate, thus reducing your nonspecific binding values. You get a cleaner assay that way.
Great, thank you. If we were unable to answer your questions or you have any further questions, please email us at help@immunochemistry.com. We will send our webinar recording within the week. Again, if you have any questions or if you have ideas for future webinars, please email us at help@immunochemistry.com. Thank you for joining us and have a great day.